Section 15.3 is about Lagrange multipliers, which is about finding global maximums and minimums of functions that have a constraint equation. For example, if I look at line 1, it says find the global extremum of a function z equals xy. Now I'm going to stop for a second. Z equals xy is a saddle. We know this. But a saddle has no high point and no low point. So if I was going to stop right there, we'd be done. But it doesn't say that. It says subject to a constraint equation. Very, very often when we're doing these kinds of problems, I'm going to be calling the function that we're trying to maximize profit. And I'm going to call the constraint equation a budget. So very, very often we're going to have some sort of budget equation that we have to live with while we're trying to make the profit as big as possible. Now, if I was going to do the whole problem, most of the time I'll only do it algebraically. I would try to draw the constraint equation. So here you can see that all the points we're actually allowed to plug in are on this ellipse. And the idea is in line 3, start drawing level curves or contours of the function and try to draw some conclusions. So you can see here that I'm using Desmos, and I can see here, for example, that A is 20. And what does that mean? That means these two blue curves, this one way up here and this one way down here, are all of the points in the plane that I can plug in and get a profit of 20. But that has nothing to do with the points I can actually plug in. In other words, my budget isn't anywhere near big enough to be able to actually make a profit of 20. So I'm going to go over to my slider, and I'm going to slide it down further, 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 further. You can see I'm getting closer to maybe a profit that I can make. Let's just go a little bit too far. So for example, here, I see the Z level here. It's right about there, is 1. I can make a profit of 1. There are 4 different ways with our budget constraint that we can make a profit of 1. Now the idea is to see what points give you the biggest profit and see which points give you the biggest loss. So what I'm going to do is try to make the profit just a little bigger. You can see as I make the profit a little bigger, that the graph goes out a little bit. And what I want to do is see if I even go just this far, that's a profit I can't get. If I go even just this far, I can do a little better. So what I want to do is just come out right to about there. And you can see that when the contour graph is tangent to my budget constraint curve, that's going to be the point where I'm making the most profit as possible. What about loss? Well, if I make the losses negative, say way out here, the good news is I can't actually lose that much money, right? My budget won't actually allow that either. So I'm going to make the losses smaller and smaller by making the Z levels negative or less and less negative, less and less negative. So I'm going down to here, going down to here, going down to here. See if I go that far. With this says I can lose -1, whatever that means. But I think I can actually, unfortunately, lose a little bit more just by pulling back a little bit. And again, all the points where I'm losing as most money as possible are points where the contour or the level curve of our function is actually tangent to the constraint curve. Now what I'd like to do is go to our whiteboard and draw a few conclusions about this sort of thing. So here we go. I've just got this sketched out. Now, what's going to happen when they're tangent? Well, they're going to have the same slope there, but slope isn't really something we worry too much about in Calc 3. We do worry about vectors, and in terms of vectors, saying they're tangent says that when I draw the gradient vector to f, let's just write down the gradient vector of f like that, and I draw the gradient vector of g. I don't know if it points out, I don't know if it points in. I'm just going to draw it pointing in just so I have some room to draw it, right? That's the gradient of g. Now, do they have to be the same vector? They absolutely do not. What we do have is that they're parallel. And remember from linear algebra what it means to be parallel. So what we're going to say is at the optimal points, we do have the following equation. We have the gradient of f, which is that green vector, has to be parallel to the gradient of g. Now, writing that they're parallel doesn't help, but what we can do is remember that two vectors are parallel if one's a scalar multiple of the other. And so what we're going to do is write down that the gradient of f is some scalar times the gradient of g. So every time we're going to have a problem of optimizing a function with a constraint equation, we're usually going to start right down here, where we write down the gradient of the function we're trying to optimize. We write down the gradient of the constraint equation, and we know there's some scalar here. By the way, that is a lambda, which is a Greek L, and in our context, that's going to be for Lagrange. So we are going to actually work out this problem in its entirety, but we are going to start right here because the picture says that the gradient of the level curve has to be equal to a scalar multiple of the gradient of the constraint equation.